Okay, so here we are. A little late, but that is to be expected. So we're going to talk a quick review over magnetism when it comes to just a single moving charge, and then we will get into current carrying wires. So here I've got a positive charge with a certain velocity to the right, and it's in a magnetic field represented by the blue dots. Now, the blue dots represent the magnetic field coming out of your screen to you. It can be represented a couple of different ways. One is like this, with the dot representing out. The other is with an X, which represents going into the page or into the board, or just whatever it's drawn on, it's going into that thing. Um, and so there is, just like with an electric field, there is a magnetic force. And that force is delivered by the magnetic field. The magnetic field is denoted here with a B. It's a vector quantity. Obviously, it has a direction because I just went through telling you how we indicate its direction. It's measured in Teslas, which the unit is just a capital T. And the magnitude of the magnetic force is the charge that's in the field. So the charge, the charge Q here, and it's the cross product of velocity and magnetic field. Now, when I say cross product, basically all you do is you multiply the two together, their magnitudes, and then you take the sine of the angle between them. Now, this tells you how much force there is, but I want to look at the direction of force. So this is where you have your first right-hand rule when it comes to magnetism. There are several, so just get ready to use your right hand a lot. So your first step when doing the right hand rule is to, one, find your right hand. Once you've done this, you're on your way to doing the right hand rule. So how it works, I've got the black arrow on here representing the velocity of my positive charge. And it's, again, going into a field that's coming out of your screen. So you've got your right hand. You point your fingers in the direction of the velocity. Okay, so I'm going to kind of show you how to do this with my own hand. Hey, so here's what you've got. I don't know if you can kind of see that, but I'm pointing my fingers in the direction of the velocity of the charge. I then curl my fingers in the direction of the magnetic field. Now my magnetic field is coming out away from me, so again, my fingers are pointed in the direction of the velocity. If I curl them this way, that's curling back towards me. The magnetic field's not coming at me. So velocity, the field is coming out like this, and so therefore my force is down. So if I'm you, I would go velocity, field, force. And so the force is pointed straight down. Bye. So as soon as this charge enters this area, it's going to experience a force that is down. We'll call that F subscript B for the magnetic force. Now, because force and velocity are perpendicular from each other, and because of the cross product, they are always going to be perpendicular to each other. In fact, force is going to be perpendicular to both velocity and the magnetic field at all times. So what's going to happen is this charge is going to get in this region, and this force down is going to cause its velocity to change direction, and change direction, and change direction, and change direction. This charge is going to take a very circular path. Reason being, let's say my charge is right here at the very edge. If you do your right-hand rule, you point your fingers in the direction of the velocity. So point your fingers with this dark gray arrow here with the V, and then curl your hand out toward you. Your thumb should be pointed to your left. So at this instant here, I have a force, I'll draw it in green, directed back in towards the center of this circle. In other words, magnetic force can be a centripetal force, and is a centripetal force when you're talking about a charge moving in a constant magnetic field. It will take a circular path, which means you can utilize those equations that we know and love. The centripetal force is equal to the mass times the centripetal acceleration, and centripetal acceleration is equal to v squared over r. Now, what about if I have a magnetic charge, or excuse me, not a magnetic charge, but a negative charge? It's this easy. The right-hand rule is for positive moving charges. Negative charges are the opposite of positive charges. Therefore, if you are dealing with a negative charge, for instance, if this charge coming in was not positive but negative, let me just go ahead and make that negative real quick, it would take a much different path. It would move like that. Because if the initial magnetic force was down when you do the right-hand rule, but you know you're dealing with a negative charge, then that charge will move up because it is the opposite of positive. Okay, so let's look at now current carrying wires. The current carrying wires create themselves a magnetic field, as does a single charge moving. So a single charge moving in a magnetic field has a force exerted on it, but a single moving charge also creates its own magnetic field. And so with a current carrying wire, it has a right-hand rule, but it's very easy. So what you do is you grab the wire with your thumb pointed in the direction of the current. So I'll show you how to do this again. Hello. So here's my wire. It's going this way. I'm going to grab it with my thumb pointed this way. Okay. Now, as I grab it, my fingers are going to indicate the direction of the field. Okay. So you grab it, and you've got a field above the wire, and then you can curl all the way down to below the wire too. So let's take a look at what that looks like. Above the wire, if I'm doing my right-hand rule, my fingers curl out, and your fingers should curl out toward you also. Therefore, that magnetic field is coming out of your screen. If it's coming out above, your fingers curl all the way around the wire, which means below the wire, the magnetic field is going in. Now, this magnetic field, we can look at this in a slightly different kind of view. Here we go. So here's my current going into the page. So this X represents current going in. Okay. Hello. So current is going into your screen. So you're going to grab the wire with your thumb pointed into your screen. Your fingers curl around like this, clockwise, all the way around. Therefore, your magnetic field is clockwise around that. Now, it is circular, and it is distance dependent. If you look, I kind of shaded these darker the closer I was to the wire because that magnetic field is stronger the closer you are to that wire. It gets weaker the further out you go. It's distance dependent, and it's an inverse relationship between those two. Now, not only does a current carrying wire create a magnetic field, but magnetic fields also exert a force on current carrying wires. So here I've got current going in again, and just like with the right-hand rule for single charges, we're going to now apply the same right-hand rule in a sense, but for a current carrying wire. Now, if you remember, when we were talking about current, we said that current was the motion of positive charges running through a circuit. Well, if you remember for our right-hand rule with magnetism, the fingers point in the velocity of a positive charge. So if we're talking about current in the conventional sense, positive charge flowing, then if I've got a wire like this with my current going in, you apply the same right-hand rule that you did with a single charge. So here we go. I'm going to point my fingers in the direction of the velocity. So my velocity is the current. So in a sense, the velocity of the charges. So my current is going in, therefore my velocity is going in. So I've pointed my fingers into the screen. Now I'm going to curl my fingers in the direction of the magnetic field. Now the magnetic field is pointed this way. So I can't curl this way, I've got to curl this way. Okay? So fingers are pointed in the direction of the current, and then curl your fingers in the direction of the magnetic field. And if you do that, you should get a force on that wire that is down. Now, what would be different if that current were out? Well, apply the right-hand rule, and you should see a different direction for the force. So here's the view of the magnetic field again created by a wire. Now I want to leave you with parallel wires. And let's start with two wires that have let's say both of their currents are going in. Okay, let's go one wire at a time. Wires create a magnetic field. Current carrying wires create a magnetic field. Wires are influenced by the force delivered by that magnetic field. Now, if I call this wire here to the left, if I call this current 1 and then I call this one current 2. Okay, wire 1 is going to create a magnetic field that is flowing clockwise. Okay, so I'm just going to kind of draw that. Okay, and it extends as far out as this wire over here. So at wire 2, it is experiencing a magnetic field that is down. Now, wire 1 is not influenced by its own magnetic field. So let's look at wire 2 now. It is also creating a magnetic field that is flowing clockwise. And it extends all the way out to wire 1. Okay. So both wires are experiencing a magnetic field that is not their own. Therefore, each wire is experiencing a force from the other wire's magnetic field. So these two wires are going to feel a force, and I want us to figure out the direction of that force. So let's look here at wire 1. If I do the right-hand rule for this wire, I point my fingers in the direction of the velocity, in this case the direction of the current. So here we go. Me again. So I point my fingers in the direction of the current. Well, my current is going in, so I've got my fingers pointed in. But now I've got to curl my fingers in the direction of the magnetic field that's on that wire. Well, the field that's on wire 1, it's the blue line. And that blue line is going up like this in a clockwise motion, and at the instant it hits that wire, its magnetic field is up. So this is a little awkward to do with your right hand, but you point your fingers in the direction of the current and then curl your fingers up, and you can see my thumb is pointing in towards the other wire. So wire 1 is experiencing a force. I'll draw it in blue. Actually, I'll draw it in green. It is experiencing a force from the magnetic field of wire 2, and it is directed towards wire 2. Okay, well, let's look at wire 2. What direction is the force on it? Well, if I do the right hand rule, if I do the right hand rule, fingers in the direction of the current is going in, curl them down, and you can see my thumb is pointed back this way. My thumb is pointed to the left, which is back towards wire 1. So it is experiencing a force this way. So these two wires are attracted to each other. If the current is running in the same direction, those two wires will be attracted to each other. Now, the magnitude of the force created by a wire is related to both the current running in the wire and also the distance from that wire. And to actually calculate what the magnitude of the magnetic field from the wire is, it looks something like this. Let me back up here. Maybe. Okay. Here we go. So to actually calculate the magnitude of the magnetic field created by a wire, it is the magnetic field equals mu naught times I times, mu naught I over 2 pi r, where r is the distance from the magnetic field. Now, as you can see from that, you've got an inverse relationship between distance and current, and the farther out I go, and that's what we did with this here, the further out you went, the weaker and weaker the magnetic field got. And you can kind of see this if you are looking at or holding a magnet like off a refrigerator or something. So the farther away you are from the refrigerator, the weaker and weaker the magnetic field strength is. And only until you actually bring that magnet close do you actually experience a force from that. So again, whoops, let me get that equation up for you again. Again, the magnetic field off a current carrying wire is mu naught I over 2 pi r. Now, mu naught is the vacuum permeability constant, and it is a constant that is given to you. You don't need to memorize it or anything. So what we're going to do is look at forces between wires, be they going the same direction or going in the opposite direction, and how we can use this magnetic field to our advantage when it comes to getting work done and things like that. So that's all I've got for you for magnetic field on charges and current carrying wires. This pretty much covers the basics. That's it. Hope you enjoyed it.